Hey guys, welcome back. I hope you had a good weekend and enjoyed some warm weather. I heard it was a little bit warmer in Denver. Um, we are going to continue our discussion on waves and how waves act. We discussed last class reflection and how off of mirrored surfaces, light waves can actually reflect. And depending on the shape of the surface, determines the angle of reflection. Today, we're going to discuss refraction. And the general definition of refraction is the bending of light when it passes from one medium to another medium. Let's see here. In part A of this investigation, if we were in class, we would be doing this, of course. We are going to take a little dish, and you'll see here on the screen this little dish, and we put in some diluted milk. So I would just get cafeteria milk and I would put some water in it to make it not super opaque, but a little bit diluted. We would then set up our light box and shine a laser beam light down the center of our milky container. And what we're wondering is if light's traveling as a wave and light is traveling through air, will light do something different when it hits milk or water? Will light do something different when it hits plastic or glass? Will light do something different when it travels through the solar system and hits an object that's filled with hydrogen or helium or lithium? So we're wondering how light behaves. Your first task is to look at this diagram. On this diagram, you will see that our light box is on the right over here, and we are going to shine a narrow laser beam of light directly down our zero line here so that the light hits the surface of the plastic and then hits the milky liquid. Your first job is to predict what is going to happen to the light when it hits this plastic surface. And then where's it going to go? Open-ended. All your answers are correct at this point. What are you thinking? Okay. This is a different question. What if instead of shining the light directly down the center line, what if we shine the light down at 30 degrees? So this center line is 0, and we've got 10, 20. At 30 degrees, we're going to shine down that laser beam. Will that light keep going exactly at 30, which is the blue arrow? Will that light bend to the 20-degree mark, so bend inward, or will that light bend to the 40-degree mark, the yellow? So go ahead and make your prediction, and we'll go from there. Well, my diagram's kind of got cut off here, but one of the things, we'll get back to our predictions in a minute, one of the things that we know about light is that light bends when it goes through different medium. Waves bend, electromagnetic waves bend. So light is an electromagnetic wave, and if it goes from one medium to the next, it'll actually bend. So this is this whole refraction in a glass of water with a pencil. So the pencil is not bending. The pencil's not broken, but it appears that way because as light bounces from the pencil to your eye, you're actually seeing through the speed of light in air. And when that light has to go through water, it slows down. This is like when you're fishing and you are looking into the water and you think, there's where the fish is, I'm going to exactly jab the fish. Well, remember that reflection is coming through the air to your eyeballs. The water affects where the fish actually is compared to what the light in the air shows you. So in this diagram, you'll see that in air, light travels about 300,000 kilometers per second. And that is a constant, the speed of light in a vacuum. Or sorry, in air, 300,000 kilometers per second. Ice is a little bit slower. Water, a little bit slower. Vegetable oil, a little bit slower. Glass, ruby, diamond. So you'll see that the speed of light changes in different medium, and then your brain should be combining that with density. The refraction of light. In general, light travels in a straight line. This occurs when light is transmitted, which is when light passes through a vacuum or a material. However, at the boundary between two transparent materials, the light can be redirected. This phenomenon is called refraction. Refraction occurs when a wave passes from one material to another, such as from air to glass. Upon entering the second material, the light travels at a higher or lower speed depending on the properties of the second material, such as temperature, pressure, and density. As the speed changes, the direction of travel through the material also changes if it hits the boundary at an angle other than perpendicular. This can be observed when a pencil inserted, wait for my thing there, and a glass of water appears to bend at the boundary where the water meets the air. So let's go back to this diagram. Now that you've read the introduction about the perpendicular, if light is traveling and hits a surface perpendicular, what will it do? If light is traveling and hits the surface at an angle, it's going to bend. Will that light bend towards the red or towards the yellow if it's going from air into water? So our question really for refraction is, how does light behave at the boundary between two different materials? I want to show you this little video. And I've muted her so you can't hear her. But this is going to show you, ooh, I should stop and go back because that was really cool. How do I do that here? I'm going to exit and play that. And I'm going to reverse it here. Okay, this will give me time to talk to you while starting. Notice perpendicular, line goes all the way through. Come in at 0, goes out at 0. Now, as the line is coming in at an angle, 10 degrees, it went out a little bit less than 10. 20, it's coming on 20. So while she's coming towards 20 here, I want you to see where it's over there. So I'm going to tell you angle of incidence 20, angle of refraction was like 12. Angle of incidence is about to hit 30. Angle of refraction is 20. Angle of incidence is about to hit 40. I'll pause it here. That 40 angle of incidence, look where it's over here, about 25. As the light, it comes in at a higher and higher angle, the refraction of the light, the bending of the light, because of the density change. Now, what she had here was light traveling through air into probably a plastic block, because that's what they would supply us with. You could use a glass block as well. And as that light comes in, so now she's going to get higher. She's going to get at 50 here. She's at 30. Now she's going even more. She's at 60, 35. So that light bends and bends and bends and bends. Pretty cool, huh? So our next idea here, if we can move our slide over, is thinking about what this tells us. Who cares? Who freaking cares about light and traveling and refracting? Well, think about the knowledge that we are trying to gain of our solar system and our universe and our multiverse and our different stars. If I have light traveling through space, which I do, and it goes through a medium that's different than space, the light will bend. And when the light bends or refracts, I will be able to tell the density of the material based on the index of refraction. I do want to play this for you, and I left him with not unmuted.
And so let's get to that analogy I was talking about a second ago. And so imagine we have a marching band that's all walking together. And so we're looking at the marching band, the trumpet players, and we're looking at them from above. And as they're marching, they're trying to keep the space between them the same. So to the person to your left or the person to your right, we want to keep that exactly the same. And so imagine that they're marching down a road. You can see that they're going to keep that spacing between them.
Now, in this diagram, notice that the marching band is going into the sand perpendicular. They're entering that surface, this surface. They're entering it perpendicular.
The same. But let's say that there's a bunch of sand in the road. And so what's going to happen to their speed as they enter into the sand? Well, the ones that enter into the sand first are going to slow down. But since they kept that distance between them the same, you can see that the angle at which we came in equals the angle at which we came out. So we don't see that refraction going on. But now let's set it up so they're marching in at an angle like this. And so they're marching across, let's say, a parking lot, and they're going to hit some sand as well. So what happens is as they come in, which one is going to start to slow down first? Well, it's going to be this one right here. They're still going to keep this distance between all of them the same. And so watch what happens as they enter into the sand. You can see they're bending like that. And so we're going from a medium where it's faster to one where it's slower. So if I put in that normal right here, what happened? This is our angle of incidence, so it's big. What happens to our angle of refraction? It's going to be small. In other words, it's approaching that normal. And so you always, when you're looking at problems with refraction, you want to imagine that marching band in your head and figure out which way it's going to go. So let's try that again. We've got a marching band now going through sand, and they're going to come out into an area where they go faster. So they're all going slow, but they're going in a straight line. Now which one's going to start to go faster first? Well, it's going to be this one right here. They're keeping the distance between them all the same, and so watch what happens now. So it's bending like that. And so if we put in that normal again, our angle.
So he was going to say the angle of incidence and the angle of refraction, different than angle of incidence and angle of reflection, because now we're talking not a bouncing back, but a bending as it goes through. I liked this diagram. It has a lot of information on it that you don't need, but some of you are going to be interested in. So I've got the normal is my perpendicular. We call that the normal. So my source of my light is my incident ray, and that incident ray is coming in at an angle. There will be a reflected ray, especially if you see where we are here. We're on the interface between air and water. So the interface between air and water, when you're out on a sunny day on your boat or fishing on a lake, the reflection, there is light that reflects back to you, which is why it's so hard to see when that light's reflecting. Also, light is being refracted. As the light moves from a less dense air into a more dense water, the angle decreases from normal. So the normal angle here is the angle of incidence. The angle of refraction is littler, smaller. This must be a really flat surface of water because the angle of reflection looks equal to the angle of incidence. This is the opposite where I'm starting in the water. So say like I'm swimming underwater and I'm looking out. So my incident ray is coming from water into air. If you're underwater looking, there will be a little bit of reflection. The incident now is from the water hitting that boundary, that medium interface between water and air, and the angle actually gets a little bit bigger. So I'm going slower and I speed up. I'm going fast and I slow down. These numbers and values, I can use algebra 2, I can use mathematics to calculate the refraction index. And the refraction index is something that's a constant for different materials. And so it can really tell me what I'm dealing with when I'm traveling through space and wondering how things, what different information I have. Here's a question I want you to answer. A light is traveling through medium 1 and enters medium 2. From this diagram, what can you tell about medium 1 and 2? Before we go, I'd like to come back to this diagram. You have a light beam coming through air at an angle of 30, an incident angle of 30 degrees. When that light beam hits a water, will it refract to 20, refract to 30, or refract to 40, going from air to water? Go ahead and answer that, and I will see you guys soon.